speaker, Linhua Sun. So Linhua Sun. So you'll be talking on a simulative study on a breakable large-scale ice floe in the presence of current. Linhua?
Please wait a minute. Okay.
Yeah. So you are not audible, Linhua.
Okay. So let's start.
Okay, start.
Okay. Hello everyone. I'm a student from Harbin Engineering University. This year is my first year of my PhD. Today I will share my idea about a simulative study on a breakable large ice floe in the presence of wave current. Okay, there are four parts about my presentation. Part one is the introduction. Okay, wave-ice interaction is an important physical process that may in part determine the fate of sea ice extended at the Arctic worms. The picture on the left was taken in reality. We can see the movement of ice under the action of wave. Yeah. And the picture on the right shows that as the distance from open water grows, the ice dune is divided into open water, MIZ, ice floe, and ice field. As we know, MIZ, marginal ice dune, it refers to the ice area closest to the open water. Which is the junction of sea ice and open water, and the effect of waves on sea ice merely occurs in the MIZ. Um, coupling is a very complex problem in ice-water interacts. The one-way interactions of a discoupled process can be described in simple terms. One is wave to ice, water to ice, and another is ice to water. When the incident wave passes through the ice, it will be attenuated by the reaction of the ice, including dissipation, scattering, and reflection. And on the other hand, the wave stress will cause the ice to break up, like a fracture ice. So in this work, we merely focus on water to ice, that is, large ice floe break up into smaller pieces under the action of wave current. Okay, part two, numerical approach. It's necessary for us to simulate water, simulated ice. And one of the method is VOF method, volume of fluid. We use this method to simulate water. VOF method is an interface tracking method based on Euler grid. In this method, the incompatible fluid components share a set of Mormon equation. And the phase volume fraction alpha is introduced. We can see the picture on the right shows that when the water phase alpha will be 1, and the air phase alpha will be 0. When the interface alpha will between from 0 to 1. And this variable is used to track the interface in the computation daemon. It means we can use this alpha to change the pressure gradient of different phases at the interface, and then update the wave surface under each time step in the Navier-Stokes equation. Because all longitudinal sections are the same along the width of tank. So when the results are validated under the single layer grid, we can extend to any ways we want. Like this picture on the right, this is the single layer grid. We can use this mode to simulate water, to simulate wave. And the picture on the left is a validation about the wave surface. The right one is numerical, and the black one is theoretical. In the simulation of water phase, two-dimensional gradient used after validation. It is tended to three-dimensional modes. And we can say there are water, there are current. And current we set two conditions, wave and the following current, wave and opposite current. And this page, I show the wave current theoretical method. And assuming the existence of a two-dimensional cylinder located on a free surface with center at origin, and there are two physical movements of the cylinder. One is perform a uniform motion along the horizontal direction with a velocity of current u, and another is by a frequency omega perform a simple harmonic wave motion in a vertical motion, and the depth is infinite. On the left, this is the draft, and on the right, we get the disparate relation, and by combining the constant wave period, the formula for wavelength change can be use this one, and we can get the amplitude. L0 means only wave, and L means wavelength. C0, we can say C0 means the wave speed, and wave speed without current. A means the amplitude with current, and A0 means only wave amplitude. Okay. After simulating the water, ice simulation is used by discrete element method. In solution, this page, it is worth noting that in solution, we set up the numerical simulation according to the theoretical simulation. A theoretical solution when applying different current velocity by controlling the wave frequency to be constant and changed under different conditions. Uh, so ice simulation is also very necessary. We use DEM method. Dispatchable bound mode can be imagined as a set of bonds with constant normal stiffness and tangential stiffness uh, are uniformly distributed in a contact plate. Uh, we can imagine many particles. These particles are bounded by some like keys, and these keys uh, can not only transmit force but also transmit moment. And when these keys between particles are broken uh, in uh, in ice, it looks like uh, ice has crack. The ice are broken. Yeah. Uh, uh, and it's worth noting that uh, the diameter of the particles is thus the thickness of the ice. Because in the numerical mode, a group of regularly arranged particles are bonded into a one layer to simulate ice. So the diameter of the particles is thus the thickness of the ice. Part three, validation. Uh, as I mentioned before, we focused on the problem about water to ice. So we use one-way coupling. And in and on the right, the flow chart shows the steps of one-way coupling. Yeah, start and we set up the fluid domain and the particle information. And we use the VOF to calculate the information about fluid, and we update the force of fluid on particles. And in DM interaction, we update the particles information between particle A to particle B. So we can see in this flow chart, we can get the fluid to ice, but we we didn't concentrate on ice to water. Okay. Uh, uh, this is a numerical layers parameters. It is worth noting that is the electric mode. This value is very small because uh, this value is from a test, HSVA test, the hamburger shape modern phasing. This is a HSVA test. We use this value from the test. So in this numerical simulation, the ice is very weak and soft. Yeah. Okay. And this video is a process of ice. Yeah. We can see that at first there is a first crack. Okay. We can see. Okay. We can see there is a first crack running through the ice along the ice, which gradually breaks up in into smaller pieces as we want. And on the left, there's a phenomenon of simulation. We can see it looks similar to the test. And on the right, mm, we can get the simulation result and the test HSVA test result. Yeah, this is the validation, and it is worth noting. Uh, it is worth noting that the small data has been abandoned because when the test the HSVA's test camera uh, in uh, in the test has limited resolution and was unable to catch some um, particularly small ice flows. So I abandoned some small data. The first part, the last part is the result. Okay. First one is draft motion of ice sheet under wave and current action. Uh, this means that waves are the main cause of ice flow fraction. But for ice draft motion, the role of current is more obvious. In addition, it's found that in numerical simulation, the draft velocity of the ice flow is greater than surface draft velocity. This is the phenomenon of the breaking process. We can say at the first stage, the cracks running through the ice along the ways could be clearly seen, and at the second picture, as the wave evolved, more and more secondary breaks, cracks can be seen, and finally, the whole broken fully developed. And in this problem, FSD means flow size distribution problem is very necessary for everyone to solve. So we use three mathematics methods to solve it. First one, probability mass function. We can obtain the data from numerical simulation. We can get probability mass function. And after this, we can sum the data and get the CDF, and finally, we by means of derivation of CDF, we can get PDF, probability density function. These pictures are the PMF, probability mass function. We can X means normalized size of S pieces, and we can see the probability of every data. And during the first one, we can get the CDF. CDF means we need sum all the probability whose size is smaller than this one. It means if we get a CDF, the CDF of size 0.2 means I need sum all the data whose size is smaller than 0.2. So the CDF's maximum is 1. And we use Weber fitting to fit this CDF. And on the right, this is the fitting formula, and we can get the parameter from fitting to Weber distribution. It's worth to explain that there are two parameter. One is the shape and another is the scale. We can see the two papers. Gamma is the shape parameter. It shows the degree of dispersion of the data, and S0 is the scale parameter. It means the average normalized size of eye species. We can see in these two situations, situation 1 and situation 2, these two situations have the same S0, but shape parameter can have can reflect the different patterns of shape. That's because gamma. Okay. After we get CDF, we use by means of derivation of CDF, we can get PDF like these two papers. And this is the result. By wave and following current, distribution of broken ice relatively uniform compared to only wave action, and average normalized size after breaking increases. And when the wave and opposing current, the distribution of broken ice size more concentrated in small scale range compared to only wave action, and the average normalized size after breaking decreases. Because this work is ongoing, so I have still some problems to be solved. One is two-way copying, because this work is only only water to ice, not ice to water. So attenuation is not it's not focused. And another one is multilayer DM. This work I use one layer particle to simulate ice. So I need to use some multilayer particles to simulate. And the three problem is the first crack. We can see the process during the video just now. And the friend, no, I'm not sure the first crack location is relative about the wavelength or not. That's all. Thank you.
Thank you, Linhua.
Thank you.
Yeah. Any questions from the audience? Any more question? Yeah, I would like to ask one question. You have the current. In one of the slide, you have given the dispersion for the relation for the current. Can you go to that slide? Some relation current.
I'm sorry. Pardon.
Uniform current and ice interaction. One slide was
uniform current.
Yeah.
Uniform current.
So can you show me that slide? Draw a relation if you.
You go to the slide of dispersion relation.
Yeah, this person relations.
Yeah. Okay. Sorry, I'm sorry.
Yeah, yes, this slide.
Yeah. Oh, okay. Just now, the PowerPoint have something wrong. Oh, sorry.
Okay, fine.
Okay.
So what I was looking at, what will happen in this case if the current is negative in this case?
Yeah.
And from here also, we
Uh,
can get a relation between the current and the speed. Can we have this only to, because you are taken
uh,
positive. Suppose I take the case U as negative, then
yeah.
it can be a situation that square root part will be 0 and L by L naught becomes 1 by 4. Can it be?
Cause
If current is negative,
yeah. L means wavelength, and L0 means uh, uh, sorry. L mean
no, I mean
L.
to say, suppose you have negative current,
Yeah.
this also can be negative. 1 plus 4 U by C naught. Can it be negative?
Yeah. If the current be 0,
Yeah,
and
if it will be 0,
yeah.
then
So
yeah,
then L will equal to L0. It means uh, because uh, L means the wavelength with
yes,
current, and
yeah,
L0
so,
L0 means a wavelength without any current. So
yeah,
so if the current velocity is equal to be 0, so
yeah.
L will equal to be L0.
Ну, купи мне этот самый дивизион секрет. Дивизион секрет, купи мне.
Yeah, and the amplitude are the same.
Yeah, same thing will happen to the amplitude also because there also that term will be 0. So that will be A by A naught will be 2. Am I correct?
Yeah. So 2 and a square
Yeah.
will be 4, and 8 will be 1. Yeah.
So maybe this part can be looked into. I was looking at that. When what will happen in case of negative current? You have although emphasized it towards the end, but from this point, perhaps something can come up. Okay. So any more questions?
Okay. Thank you.
Yeah. If there are no questions, let's thank Linhua Sun. Thank you. So you can stop sharing your screen now.